Hello everyone, myself Soumya BJ, Assistant Professor, Department of ACE, SJBIT. In this session, I am discussing about the Module 5 topic of microwave and antennas. Module 5 is about loop and horn antennas and antenna types. These are the topics that are to be covered in Module 5. In this session, I will be discussing about helical antenna. Coming to the helical antenna, this is the one which is actually wounded in the form of a helix. That is why the name helical antenna is been given. As you can see here, this has been wounded in the form of a helix, and the middle one dotted line whatever we are seeing is the helix axis, and this actually represents the capital D represents the diameter of this helix, and this is S represents the spacing between these individual loops that is created by the helix, and small d represents this diameter of this material of the helix, and one complete loop corresponds to the length capital L, and coming to the total axial length which is represented as A, it is given by N into capital S. Similarly, total length of the wire is given by N into capital L, and these dimensions can be represented in the form of this triangle, in which the hypotenuse represents the capital L and the adjacent sides and the remaining sides, the two sides are represented as S, and the other one is circumference C, which is equal to pi into d. And this length corresponding to this representation in the form of a triangle is given by square root of S square plus C square, and the angle formed between this hypotenuse and the adjacent side is given by alpha, and it is tan inverse of S divided by pi d, the ratio opposite side divided by the adjacent side. Opposite side is S, the adjacent side is C, that is pi d. So, tan inverse of S by pi d or tan inverse of S by C. Now, coming to the special cases which are being taken with respect to this alpha. In the first case, when alpha is equal to 0 degree, there is no angular representation and this value of S becomes 0. And in such a case, now this helical antenna replaces the loop antenna. Similarly, coming to the case 2, in which the angle is 90 degree, in such a case this d value, that is the diameter of this loop, will become 0, and this helical antenna results in linear antenna. Helical antenna results in linear antenna. I repeat, the antenna which is wounded in the form of a helix is called as helical antenna, and corresponding to the dimensions of the helical antenna, we can represent the diameter as d, and this is the spacing represented as S, one complete loop represented as L, and the diameter of the wire is d, and A represents the axial length which is given by N into S, and it can be represented in the form of a triangle, in which capital L represents the hypotenuse and the remaining sides are S and C, and correspondingly L is given by square root of S square plus C square, and the angle formed between the hypotenuse and the adjacent side is given by alpha is equal to tan inverse of S by pi d, that is equal to tan inverse of S by C. And there are special cases with respect to this alpha value. When alpha is equal to 0, this loop antenna is replaced for helical antenna. Similarly, when alpha is equal to 90 degree, the linear antenna replaces the helical antenna. Now, let us discuss about general characteristics of the helical antenna. This helical antenna is used as a frequency shifter as well as a polarizer, and can be used as a feed antenna. Helical antenna can be used as a frequency shifter, it can be used as a polarizer, as well as it can be used as a feed antenna. and helix is a basic 3-dimensional geometric form, and it combines the geometric forms of a straight line, a circle and a cylinder. It is a basic 3D geometric form, and it combines the geometric forms of a straight line, a circle and a cylinder. And as we just now discussed, the D represents the diameter of the helix from center to center, and C is the circumference of the helix, which can be represented as pi d. S is the spacing between the turns, and alpha can be represented as pitch angle. L is length of one complete turn, and N is the number of turns. A is the axial length, which is represented as N into S. D is the diameter of the helix conductor. Helix is a basic 3D geometric form. It combines the geometric forms of straight line, a circle and a cylinder. Accordingly, the dimensions can be represented as D. D is the diameter of the helix. C is the circumference of the helix. S is the spacing between the turns. Alpha is the pitch angle. L is the length of one turn. N is the number of turns. A is the axial length, and D is the diameter of the helix conductor. Now coming to the different modes of operation of the helical antenna, there are two basic modes, transmission mode and radiation mode. First, let us discuss about the radiation mode. In radiation mode, based on the circumference, there are three modes. One I call it as normal mode, another I call it as axial mode, another is called as conical mode. And when I tell normal mode, the circumference will be very much less than lambda. C is very much less than lambda, that is in normal mode. And coming to the axial mode, C will be almost equal to lambda. This is axial mode. And coming to the conical mode, the C will be very much greater than lambda, or I can tell that C is almost equal to N into lambda. C is almost equal to N into lambda. There are two modes of operation of the helical antenna. One is the transmission mode, another is the radiation mode. In radiation mode, based on the circumference, there are three modes. One is normal mode, in which C is very much less than lambda. Another one is axial mode, in which C is almost equal to lambda. And third one is a conical mode, in which C is very much greater than lambda, or we can tell that C is almost equal to N lambda. Okay, these are the representations of different modes of the helical antenna. This is the normal mode, in which C is very much less than lambda. This is how the radiation pattern, the circumference, as you can see here, C is less than lambda, that is why we are having a smaller loops here, and this is how the radiation pattern looks like. Coming to the axial mode, in which C is almost equal to lambda, this is how the radiation pattern looks like. It is more directed, and there are only little side lobes. And coming to the conical mode, in which C is almost equal to N lambda, where N value may be 2, 3, 4, etc. In this case, as you can see, the direction is more towards the left and right side, and the side lobe is in the middle. It is more directed towards the left and the right direction, and there is a small side lobe in the middle. This axial mode, in which C is almost equal to lambda, and the normal mode when C is very much less than lambda, these are the two cases which are actually more frequently used in the helical antenna. And this axial mode is basically used whenever we go for circular polarization, and whenever we go for linear polarization, we go for normal mode. It means in the circular polarization, we use the axial mode, and whenever we go for linear polarization, we use the normal mode. Now let us discuss about the axial mode helical antennas ground plane characteristics. Whenever there is a flat ground plane which may be circular or square, this is a flat ground plane, and this spacing is the length is actually 3/4 lambda, on which this helical antenna is being placed. And in such a case, whenever there is a flat ground plane, and we tell that there is a low front to back ratio, because in this case D is almost equal to lambda by pi, and in this flat ground plane, for the length equal to 3 by 4 lambda, we tell that there is a low front to back ratio. Coming to the next, in which there is a ground plane which is not circular or square. There is a cupped ground plane. There is a ground plane which is in the cup shape, and here in this case also the d is almost equal to lambda by pi, and in this case we have got medium front to back ratio, and if you want to have a high front to back ratio, the ground plane has to be in the form of a deep conical form, which is actually covering the entire helical antenna, and the spacing between this deep conical is d is equal to square root of 2.5 n s lambda into lambda. This is the one which is having high front to back ratio. Whenever we go for flat ground plane, we have low front to back ratio. Whenever we go for deep conical ground plane, we have high front to back ratio, and whenever we want to go for medium front to back ratio, we use shallow cupped ground plane. The important parameters of helical antenna are beam width, gain, impedance and axial ratio. Let us first discuss about the parameter, that is impedance of this axial mode helical antenna. For axial field, the input impedance should be equal to 140 multiplied with C lambda, and the unit is ohms. And for peripheral field, the R is almost equal to 150 divided by square root of C lambda, and the unit is ohms. Tapered microstrip line is used for input impedance matching, and for such a case the conditions for circular polarization will be the C lambda should be greater than or equal to 0.8 or less than or equal to 1.2. Similarly, alpha should be greater than or equal to 12 degree and should be less than or equal to 14 degree, and n should be greater than or equal to 4. Now let us discuss about the gain of this axial mode helical antenna. Whenever I tell half power beam width, the half power beam width is almost equal to 52 divided by C lambda into square root of n s lambda in degrees, and beam width between first nulls is almost equal to 115 divided by C lambda into square root of n s lambda. Beam width between first nulls is 2 times the half power beam width, and the directivity is given by 32,400 divided by half power beam width square. And there is one more formula for directivity which is given by 12 C lambda square into n into s lambda. The gain is given by eta times the directivity, where the eta is the efficiency, which is equal to, which is standard value is 60% basically. So half power beam width is 52 divided by C lambda square root of n s lambda, and beam width in first null is 115 divided by C lambda square root of n s lambda. Directivity is 32,400 divided by half power beam width square, and the formula is given by 12 C lambda square n s lambda, and gain can be calculated as eta times the directivity. The eta value is 60% for helical antenna. Now let us discuss about the design of the axial mode helical antenna. This is our helical antenna, which is having dimensions as L0, S and C. The angle, pitch angle is alpha. For this design of axial mode helical antenna, the given data is directivity. It means we need to have a directivity of 24 dBi. If I convert this to the normal value, the value will be 251.19. Now for axial mode helical antenna, let us assume that C lambda is equal to 1.05, which is in the range of 0.8 to 1.2, and alpha can be assumed as 12.7 degrees, since it has to be in the range of 12 degree to 14 degree. Now first calculate S lambda. S lambda is given by C lambda into tan alpha. After substituting C lambda as 1.05 and tan of 12.7, we get the value as 0.2366. Now from this, let us find the directivity, which is given by let us use the directivity formula, that is 12 C lambda square n into S lambda. In this equation, we know what is the desired directivity. It is 251.19. We know C lambda as well as we know S lambda as well. From this, we will find out what is the n value. N is given by 251.19 divided by 12 into 0.2366 into 1.05 square, that is equal to 80. So number of turns of the helical antenna, that is equal to 80. This is how we design the axial mode helical antenna. This is actually the measured field patterns of axial mode helical antenna for 6 turns and pitch angle alpha is equal to 14 degree. As you can see on all these diagrams, only thing that is actually varying is the C lambda value and the frequency value. C lambda is 0.66 and the frequency 276 megahertz. This is how the radiation pattern looks like. As this value C lambda is 0.73, 0.85, as it increases, we get a more directed pattern, but when it value reaches up to 1.35 and frequency is 560 megahertz, we get the pattern which is similar to 0.66. It means for this radiation pattern for C by lambda from 0.73 to 1.22 is actually the desirable one, and below this and after this are not the desirable radiation patterns. This is how the effect on the number of turns. As you can see here, this is the one which is having more number of turns, and this is the radiation pattern, it is more directed. The number of turns is reduced by 8, this is the radiation pattern, next 6, next 4, 2. As you know, as the number of turns is less, the radiation pattern is broader, it is not more directed, but as it is being increased, the radiation pattern becomes more directed. This is the pattern of a single turn helical antenna. These two actually representing the normal mode and the end fire mode. This is how the end fire mode radiation pattern looks like, and this is the one which is actually representing the normal mode, which is a broader one. This is the practical representation for this helical antenna, and this is how the radiation pattern of the helical antenna. Again, this slide is with respect to the normal mode and the axial mode. This is the radiation pattern of the normal mode, and this is the radiation pattern of the axial mode, and it may be viewed as a derivative of the dipole or the monopole, but it can also be considered as a derivative of a loop. Now coming to the feed design for the helical antenna, the height is given by W by 377 divided by square root of epsilon Z naught minus 2. Here W is the width of the strip starting at the feed, and epsilon R is dielectric constant of the dielectric slab, and Z naught is the characteristic impedance of the input transmission line. The helix transitions from the strip to the regular Y gradually decreases during the 1/4 to 1/2 turn. And one more thing that we need to discuss with respect to the helical antenna is the formula corresponding to the axial ratio. The axial ratio is given by 2n plus 1 divided by 2n, where capital N represents the number of loops. Okay, this is about the helical antenna, how the helical antenna looks like, what are the dimensions corresponding to the helical antenna, how actually we characterize the parameters, how and what are the radiation patterns with respect to different modes of operations of the helical antenna. In the next section, we will discuss about one more type of antenna. Thank you.